Okay, so I have been looking at the notes, and I think what we're going to try to do in this video is to get through the rest of the material in Unit 8, Chapter 8. Now, I'm going to just tell you something up front about this. This next section has a lot of complex mechanisms in it, and they, in my opinion, are well beyond the scope of this course. What is important about this material is that you pay attention to what the reagents do. I'll explain a little bit about how some of the mechanisms work, but again, just remember that some of these are somewhat complex, and I will emphasize the portions that you need to know as we're going through and talking about this. Okay, so the next thing that was on the list to talk about is the addition of oxygen into alkenes. Now, the first reagent we're going to talk about is potassium permanganate. Now, this is a very powerful reagent. It will react with alkenes to produce 1,2-diols, and when heated will undergo what's called oxidative cleavage. This is a reagent that is really not used very frequently, okay, in doing these kinds of conversions, because it oftentimes overreacts and reacts with way too many things. And so it's an extremely powerful compound in that it's not very selective as with what it reacts with either. And there are all kinds of other things that potassium permanganate can react with that you'll find about in the next semester. But if it does work, well, in an ideal case, what you're hoping is going to happen is that the potassium permanganate could react, let's say, with this alkene, and here I've shown one, you have a hydrogen on this side, and here you have a methyl group here. And if you treat this with potassium permanganate and cold base, well, what you will end up with is this 1,2 vicinal diol. That is, the OHs are on adjacent carbons. And what's important here is that you get syn addition, meaning the two OHs are on the same face of that alkene. Now, mechanistically, what is going on here, and I apologize, I kind of scribbled on this. I decided I would give you a little bit of detail here, is I've drawn out what a permanganate ion looks like, and here is the alkene. And mechanistically, what happens is when the alkene reacts with this, one of the lone pairs in the oxygen reacts with one of the carbons on one side of the pi bond, and then those electrons in the pi bond actually go up and react with one of the oxygens in the permanganate, and then those electrons go on to the manganese. So you end up with a complex that looks something like this. Now, again, I'm not interested in that you really reproduce this. I'm more interested in you understand that you see that the two oxygens are coming from the permanganate and that they're on the same face. And when you treat this with water and base, it effectively reacts with the manganese and effectively kicks it out as manganese dioxide, and you end up with your diol here. Now, that's if everything goes according to plan. What will often happen with this particular reagent is that it will do side reactions. So if you took the same compound, but you did this reaction hot, what would actually happen is that the reaction would undergo oxidative cleavage, and you would end up forming it would initially you would have a diol, but then the diol would continue to react with the permanganate, and that would result in effectively cutting this double bond here in half and inserting oxygens. And that's what I want you to think about when you hear about oxidative cleavage, is you're effectively cutting the double bond in half and inserting oxygens in there. So let's do that. So I'm going to just insert 2 oxygens into here like so. Now, that is giving you 2 separate molecules. The thing you have to be aware of with potassium permanganate, and you guys should be able to classify these 2 molecules. I've got a ketone here, and this is an aldehyde, okay? it turns out that aldehydes will continue to react with the potassium permanganate. So the reaction isn't done. So you'll end up with this molecule here. That's fine. The ketone will stick around. But all the aldehydes will also get oxidized and they will react with the potassium permanganate. And when they do, they end up being converted into carboxylic acids. So you end up not isolating the aldehyde, but in fact isolating carboxylic acid that came from the aldehyde and a corresponding ketone. Now, if we were to do this reaction with, let's say, cyclic compound, all right, again, the same kind of thing. You want to draw in your hydrogens here so that you recognize what's going to happen. And you're going to cut that double bond in half. So when I draw the product out, I'm going to draw this double bond here so it's a little bit longer, and I'm going to put those two oxygens in place. And you can clearly see that I have two aldehydes. So what's going to happen is that's going to get further oxidized in the KMNO4 because it was done hot to the corresponding carboxylic acid. Okay, and so you would end up with this acyclic compound. Now that looks weird, and you should get comfortable with counting your carbons here for these kinds of systems. So I've got a 6-carbon system. So if you were to unfurl that, what would that look like? 1, 2, 3, 4, 5, 6 carbons. This is the same thing as that molecule. So you've got to get comfortable doing this when you're working on your homework. The role of the acid here is to effectively neutralize the base and to protonate any carboxylic acids that are generated. Now, that being said, I never used this reagent for a single reaction in graduate school. The only time we ever used KMNO4 was to identify spots on a thin layer chromatography plate, which you guys may remember that experiment at the beginning of the semester when you were doing the TLC. And it is very useful for that, okay, because it will show compounds readily. But as a reagent, it's not terribly useful because of all of those side reactions. Now, a reagent that is much more selective is this compound, osmium tetroxide. It is much less reactive than potassium permanganate and will not undergo oxidative cleavage. So if you want to make the diol and you do not want to have to worry about oxidative cleavage at all, well, then this is the reagent of choice. So if you were to take this cyclohexene with osmium tetroxide, and this is sodium hydrogen sulfite, its role is to basically neutralize everything at the end. It acts as a reducing agent. And it will end up producing the cis diol, okay? And again, if I'd have drawn those down, that would have been the same compound because there's a plane of symmetry here. But you want to be aware of it that there was another functional group here that you would need to consider the other isomer that was produced. Like if there was another substituent present in the ring, well, then that would, of course, mean that you would need to consider the other isomer as well with the 2 OHs drawn down. But in this case, because it's not chiral, because of the plane of symmetry here, you don't have that issue, okay? Because this is a meso compound. What's important is that this is syn addition. Okay, now you may be like, okay, well, why did we even talk about potassium permanganate? Let's just pull this out. Well, the problem is this is one of the most toxic substances known. Osmium is incredibly dangerous. Very small quantities can kill you. So this is another example of a really nice reaction, but the reagent is extremely toxic. So there are other methods to make diols that we're going to talk about when we get to chapter 11, but just be aware that these are two options that are open to you. I'm just mentioning a little bit of the nuances of some of this chemistry that the book doesn't necessarily go into. Now, as far as practical oxidations, like the really important oxidative process in this section is ozonolysis. Now, ozone, as you may remember from general chemistry, is O3. And this is easy to make, okay? All you need is an electrical source and air, okay? And so if you've spent any time next to a Xerox machine, you have smelled ozone, okay? So this is easy to make. This will oxidatively cleave alkenes and will not over-oxidize the resulting aldehyde and carboxylic acid. So this is one that will do the cleavage but won't over-oxidize. And this is a very easy, cheap reagent to use. And so this makes it a particularly attractive reagent in organic chemistry. So for instance, if you had this this alkene here, and I've picked one where I've got 2 hydrogens here, so this is cis-2-butene. You would treat this with ozone, and then the workup is you use either dimethyl sulfide or zinc and acetic acid. These effectively take out one of the oxygens from the ozonide that is produced in this particular system. And I am going to just draw this out for you just so that you can say that you have seen what it looks like a little bit. So the way that it works is that ozone, if we draw out its Lewis structure, looks something like this. So you've got one oxygen with a negative charge and one with a positive formal charge. And similar to potassium permanganate, the ozone begins to react with the pi bond, and then the pi electron, or the one carbon on one side of the pi bond, and the pi electrons react with the other oxygen on the other side to dissipate the positive charge. So you end up forming this 5-membered ring with oxygen. Okay. And this particular system here is relatively unstable, and it undergoes a rearrangement. Okay, in solution. This has been studied quite a bit. It turns out that the oxygen-oxygen single bond is quite weak, and so it turns out that the carbon-carbon bond actually ends up reacting with the oxygen here in the middle, and then one of these 2 bonds ends up going around and then reacting with the other carbon on the other side. The net result of that is this species. It looks like this, okay? And so ultimately you end up with this. And this is where you are at step 1. And the dimethyl sulfide is attracted to, again, the oxygens here that has this relatively weak oxygen-oxygen bond. So dimethyl sulfide will actually go in and react with that one of those oxygens, okay? And that oxygen will in turn release its electrons to form a pi bond with this oxygen. This oxygen will release, this bond will break to form a carbonyl here between the carbon and this oxygen, and then those electrons will go on to the oxygen that's left over. So the net result here is that you end up with one molecule. Again, there's a hydrogen here and a hydrogen here. That's an aldehyde. And then this molecule here, which is also an aldehyde. And then a molecule of dimethyl sulfoxide, or DMSO. But these are the important compounds that you're getting out of that. Now, the nice thing about this is that we're able to stop at the aldehyde and it doesn't go any further. And so that makes this a very, very nice way to do oxidative cleavage. And the reaction is relatively fast. Now, it gets even sexier if you start considering cyclic systems. So here, again, remember you've got those 2 hydrogen atoms there. if this were to undergo oxidative cleavage, and I'm not going to go through and draw the mechanism out again, but you guys know what that means. It means that double bond there is going to effectively have oxygen inserted into it. You're able to get that aldehyde. And again, be sure that you're able to unfurl these, okay, and look at the acyclic form. And recognize that those two compounds are the same thing, okay? And there's several questions about this in the homework. And there is a fairly nice synthesis problem that is on page 20 of my notes that's available online. And I would look at that question. But to save time, I kind of want to get on with talking about this so I can get the rest of the material knocked out for this particular chapter. So what about alkynes? How are they affected by these oxidizing agents? Well, it turns out that alkynes, whether you react them with potassium permanganate or ozone, will undergo oxidative cleavage and will by default turn into carboxylic acids, okay? So what you want to be thinking about here is that if, let's say you treat this with KMNO4, you end up with this diol, okay? But that diol will react with potassium permanganate again, okay? And so you've got another bond right here. And so if the permanganate does its business a second time here, you end up with this. So you've got oxygen, manganese, oxygen, manganese, double bond, double bond. Well, this right here, that is effectively going to weaken this bond to the extent where it is going to release its electrons, okay? So you're going to get a rearrangement. So this, this bond is going to shift over here so that you now have a carbonyl that is formed. These electrons then go on to the manganese, and then these electrons now form a carbonyl here with this carbon. And so it ends up releasing an equivalent of manganese dioxide. So what you end up with here is effectively 2 molecules of acetic acid, okay, and an equivalent of manganese dioxide. But you would have predicted that anyway, just have counting 1, 2, 3, 4. If you'd have split that like so, you're like, okay, I've got a 2-carbon system here. So that means this carbon here where the triple bond is now going to be 1 carboxylic acid, and then on the other side, another carboxylic acid. Okay, so instead of just leaving it with oxygen, you would insert the OHs there as well. Now, if this is a terminal system, well, you need to consider this as well. So again, if we were to do that same kind of cleavage, well, you've got one equivalent of a 1, 2, 3 carbon system, which is going to be 1 carboxylic acid. But then your other system is going to have a carboxylic acid and an aldehyde. Now, again, remember what I said about KMNO4 and aldehydes is that those are going to keep reacting. So this is formic acid. It will react again to form carbonic acid. And carbonic acid, you should remember from general chemistry, decomposes into carbon dioxide and water. And so this is going to go off as a gas. And so this carbon effectively gets cut out from a terminal alkyne when you treat it with potassium permanganate, okay, or ozone for that matter. Okay, so that's all the stuff about oxidative additions I wanted to talk about. There was a lot of things in there. The main one to focus on is the ozonolysis. That's the most useful technique of that set. Don't get too stressed out about the mechanisms. Focus again more on the products, but there were several reactions in there that I just mentioned. And the last thing I want to talk about is the addition of a species that's called a carbene. Now, carbenes are similar to carbocations in that they are electron deficient, but they are effectively neutral. Now, the way that you can make a carbene is if you take a carbon that's already electron deficient, that has a hydrogen on it, like chloroform here, and have that react with that hydrogen. So when it removes that hydrogen, you end up with this carbanion, and chlorine is a good leaving group, and in this particular case, the chlorine actually just leaves the system. And so you are left with this rather unusual looking molecule. Now, if you calculate the formal charge on this carbon, you have 4 valence electrons for the carbon. It has 2 bonds and 2 lone electrons, and it has a 0 formal charge. So this is the carbene that I was talking about a moment ago. Now, carbenes are highly reactive. Okay, they will, even though it's neutral, it's a highly reactive system, and it's going to look for something to add into. Okay, now the type of systems that it adds into is, well, alkenes. So if you had this particular compound, again, if you take potassium hydroxide with chloroform, that's going to result in the formation of that carbene system that we saw just a moment ago. And the way that that works is it turns out that these electrons react with one side, okay, of the pi bond, and then the pi electrons actually wrap back around and attack the other side of that carbon. And this is a concerted mechanism in that it occurs all in one step. And so that means in order to form a 3-membered ring that, well, this has to occur on the same face, and you end up with a cyclopropyl system. This chemistry has been exploited quite a bit recently. It turns out that a lot of pharmaceuticals now have these types of 3-membered rings in them. The problem is these chlorines. It turns out that chlorine bonded to carbon is generally fairly toxic and is not used for a lot of compounds. Now, there are some examples out there. One that comes to mind is the sweetener sucralose, which is basically chlorinated sugar. But most chlorinated compounds of carbon are fairly toxic. So the goal here is this would be really great if we didn't have these 2 chlorines here, okay? So a modern version of this reaction is what is known as the Simmons-Smith reaction. So if you take diiodomethane and you treat it with zinc and copper, what that does is the zinc ends up inserting in between one of the iodides and the carbon. So it does what's called a metal halogen exchange. And when it does this, it effectively will give its electrons to the carbon and kick out the iodide. So you end up with a carbene that has no halogens on it, okay? And you get a equivalent of zinc iodide. Now, if we were to do that here with the same cyclohexene system, you would be able to add in now a carbene that does not have those halogens. And if that did the same kind of reaction that we saw earlier, well, you'll be able to add on a 3-membered cyclopropane ring. And again, syn addition with carbenes. Okay, now I know that was a lot of information to get through, but I've got to start moving. We need to get into chapter 9. this week, which is on NMR. There is a PowerPoint for that, but I've decided what I'm going to do first is we're going to do a crash course in NMR. I hate saying that, but you know, that's what I'm going to do first. I'm going to give you an overview. Let's call it overview of NMR, how it works, give you some pointers at the beginning, and then we're going to go through that PowerPoint quickly. I'm not going to spend a lot of time on the theory, and I would like to get through most of that within 2 lectures. The main thing that you leave chapter 9 with is you have a good idea about how proton and carbon NMR is used to identify structure, and I'm going to emphasize that over talking about the theory behind why NMR works the way that it does. There are entire courses on NMR that can explain it, so I'm going to be focused much more on the application side of things. Okay, guys, so I hope everybody's doing okay out there. If you've got any questions or comments, please leave them in the comment section or send me an email about any of this material. Again, chapter 8 is the largest chapter in the textbook, and there is a lot of reactions in here. So please make for sure that you're staying on top of your homework, both online and in the textbook. And that's it, guys, and I will talk to you guys again soon. Take care. Bye.